Good morning, chemistry fans. I am back with my trusty lab assistant. We want to demonstrate some of the reaction rate stuff that we talked about. And so that you can see it, of course, reaction rate, as we mentioned, really is just what it says. How fast does a reaction or slow does a reaction go? And you generally look at it by watching the disappearance or measuring at different times the disappearance of the reactants that you started with. So it's kind of a concentration change over time deal. And you can influence those factors, and that's some of the things we're going to talk about. And it all revolves around collision theory, which is that statement that for a reaction to occur, the molecules must be, or compounds must be colliding at the appropriate energy level and in the appropriate orientation so that the activated complex gets bound and the reaction occurs. And whether it's a combustion or synthesis, single replacement, double replacement, whatever, that it all occurs, and you can do things to change that. So our first thing is to look at concentration, which is one of the factors. What I have here in this beaker is just plain old high-V pure cane granulated sugar. And what I have in this beaker is just some 1 molar sulfuric acid. Now, sulfuric acid, when you mix it with sugar, essentially it dehydrates it. What you get produced is some water, some carbon dioxide gas will come off, and the sugar will be broken down into its basic carbon, as you're going to see here in a moment. And it's a very exothermic. We haven't talked about that yet, but it releases a lot of energy. You're going to see that, and it's going to become very hot and everything else. Now, the whole idea behind concentration is the more particles you have, the more, again, all of this is the odds of reaching activation energy and getting the reaction going, and the rate at which it does so. And in that theory of concentration, then, if you have more particles colliding, you've got a greater chance of reaching activation energy and have the reaction occur, okay? So the first thing I'm going to do is I'm just going to take this 1 molar stuff and I'm going to pour it in with the sugar, and we can kind of watch the reaction. Okay. And oh, how exciting that is. Now this is 1 molar stuff. So again, 1 mole per liter kind of stuff, and it's very exciting. Now hold up. What I have here is the stock solution jar of sulfuric acid, which is 18 mole. So 18 moles per liter. So it's more concentrated. Now, while this reaction may be doing a little something over time, it ain't going very fast. So how about if we pour in some of the fully concentrated stock solution? See if that speeds up the reaction, because we're putting more sulfuric acid particles in there to collide with the sugar particles and get things going, we hope. And there we go. And you can see the reaction got much more vigorous. You can see the carbon dioxide and the heat and the stuff coming off. You can see the carbon that got formed. I'm standing back a little because really, if you've ever burnt sugar or something in the kitchen, it's got, or, it's kind of the same organic compounds as you and stuff like that, but it smells like burnt sugar, and it's just a nasty little odor as it caramelized and stuff and did the carbon. And I'm not sure if you can see it from your view, but it's still reacting in there because the carbon cylinder, whatever you want to call it, is slowly rising as more and more goes. And of course, as the gas is pushing up and trying to escape and stuff along that line. But we can see immediately how quickly the reaction changed when we put in a more concentrated solution. More particles, more collisions, better chance of getting to activation energy. and having that reaction occur. Conversely, then, you know, that's how you slow something down. Use less concentrations, less concentrated, less number of particles pounding into each other, and less chance of a collision. Okay. So I'm going to pause our exciting video here for a second, and I'm going to clean up and set up for our next demonstration, which will be one on catalysts. Hold up. Okay, we are back, and I've got another demonstration set up here for catalysts. Now, we're going to demonstrate. So we just demonstrated concentration. It still smells like a lot of burnt sugar around here, and yay. The one I'm not going to demonstrate today is temperature. That's easy. We're going to see that in labs that we do over the next day or so. Anyhow, temperature makes a whole lot of sense. Temperature is, again, average speed of the molecules. So in theory, if you put more energy in, more kinetic energy, they're moving faster. Their odds of colliding at activation energy in the right orientation are much greater. So heat, temperature, you know, increasing the heat and bringing up a reaction temperature will always speed it up, and cooling something will always slow down the reaction rate. So what we're demonstrating here is a catalyst. Now, what makes a catalyst different, if you remember from our notes, is that number one, a catalyst can only speed up a reaction. It can never slow it down. So that's the one factor that always just speeds it up. How it does so is by not being directly involved in the reaction, it just guides the reaction. And so what a catalyst does, and if you think to biology about enzymes and their actions, it's the same thing. What the catalyst is really doing is, now what they'll say in the chemistry text is that it is lowering the activation energy. So it is dropping that activation energy hill and making it easier for the reaction to occur at a lower energy. And it's really not physically lowering it. What it is, it's falsely lowering it in the fact that one of the substances can bind to the catalyst that orients it and just makes it easier to go. And so it does occur at lower energy levels than normal. Okay. The other key thing about the catalyst, besides the fact that it can only speed up, and it will just say it lowers the activation energy of the reaction by working as a mediator, a negotiator, whatever, is that it is never a part of the reaction. I mean, it assists in the reaction, but it's never part of the products. It doesn't become involved. It just assists it to go faster. And then when the reaction is all over, the catalyst is still there. It can be removed and filtered out of the reaction and used over and over again. Some catalysts, like some with the rare metal rhodium and stuff, can be thousands of dollars expensive stuff, and so you want to get multiple use out of it. What I have here in this bottle is, and this is a Members Mark purified water, mineral enhanced for taste, blah, blah, blah. I have some hydrogen peroxide in here. Now, hydrogen peroxide in and of itself will decompose over time to make water and oxygen gas. Now, this is not the peroxide you might have in the cupboard at home for bleaching your hair and putting on boo-boos and doing whatever. That stuff that you buy at the store is 3%, lasts about a year, and then it's not really very good after that because really it has decomposed into more, really pretty much water and very little peroxide. This is lab grade 30% stuff, okay? So as I already told you, 3% stuff will take at least a year in your bottle to decompose. This will take a whole lot longer. And so we could sit and watch this for a minute and get really thrilled of not really seeing the oxygen release and everything else. What I have in this jar is manganese dioxide. Now, manganese dioxide is a great catalyst for this reaction. And I'll show you what it looks like here. It's just it looks like a black powder, black fine powder. And what it's going to do is it's going to speed up this reaction when I toss it in with the hydrogen peroxide. And you'll then see, and again, you'll see the reaction speed up dramatically. You'll see the release of the oxygen gas, and this one is also exothermic. And so it releases a lot of heat while it does so. In the end, while the peroxide is decomposed into water and the oxygen gas has been released, what you'll see in the end is you'll see this black looking water liquid stuff. If we really wanted to, we could then just heat it up and boil away the water and get the manganese dioxide back. We're not going to because it's not an expensive catalyst and it doesn't take much, but that's what we have going on. So I'm going to put it in here. You're going to see the reaction go rapidly. I'm going to step back rapidly because, you know, it's a very vigorous reaction and I don't want stuff splattering on me. There you go. You can see that rapid decomposition. If the camera lets you, you can see it bubbling very vigorously. Inside the reaction, you can see the stuff coming off of it as it releases the gas. And then what I'll show you here as it slows down and gets done, and you might be able to see it on the camera, but I'll show you here in a second, okay, is that you can kind of see the label has pulled away because the bottle has shrunk. That's how vigorous the reaction was. And the amount of, the exothermic, the amount of heat that was released by the bottle actually melted, shrunk the plastic down. And I'm just trying to be careful because it is warm. But you can see, I'll bring this closer, and you can see how, you know, that's falling apart. This is really shrunk down and getting, and was pretty exciting in how it did. So that's how the catalyst worked. And you can see then that really we could just evaporate the water off and get that manganese dioxide back. All right, I have one more to show you on surface area, but again, I need to pause and clean up, so I'll be with you in a second. All right, we're back again. And I've got kind of the lights off on this one because we're working a little bit. We're going to be working with some flame and stuff on this to show you this. Now, the last one we're going to demonstrate is surface area. This is the one that young chemistry students often have the hardest time explaining. They know what they're talking about, they don't say it right. Okay? So here's the best example, again, as I talk about from our notes. And you would know this. Think of a big old block of ice. If I set that big old block of ice outside, it will eventually melt. The sun will hit it, and it will do its thing, and it will eventually melt. If I wanted to make it melt faster, I would chop it up and expose more surface area to the sun, and it will melt faster. And that shouldn't be a shock to anyone. Crushed ice will melt faster than a big block of ice. When you're starting to have bonfire in the backyard, you don't start with a big old log, you start with kindling because there's more surface area available to react. So that's the idea. We're not changing the number of particles or particle. It's even though as you chop up a block of ice, it seems like you're getting more ice and smaller ice. You're not changing the number of particles. You're just exposing more particles. You have more surface area. And again, collision theory. You want to increase the odds of hitting not only at the right energy level, but at the right orientation. And if you have more particles exposed, with more surface area exposed, more stuff to collide with and everything else, like I said, more sun to work and hit the ice. The block of the ice is taking long because all that stuff that's inside the initial edges of the cube, they have to melt away before that surface area can get exposed to the sun and let the sun allow it to melt. And that's true of anything. Okay, so the more surface area you have, okay, then you have more size to collide with and a greater chance of hitting activation energy in the right orientation. So let's demonstrate that. What I have in this beaker is just some very simple Coffee Mate, the original, non-dairy creamer. Non-dairy creamer is just fat. It's just an organic compound, which means that as a fat, as a hydrocarbon, all it will do is go through a combustion reaction. There's oxygen in the air. I give it a little spark with a match, and non-dairy creamer should burn in a combustion reaction. So let's watch this and see how that works. So I got to be very careful because it is a combustion reaction. So I'm going to let the match go, and I'm going to drop it into the non-dairy creamer. And whoa, had to be careful. Nothing really happened. Let me try again, one more time. Get the match going, back away a little because it could be dangerous. Ho! Okay. Doesn't seem to be doing much. What I have going here, although it's a little hard to see for me from on the camera in the background because of some of the ambient light in the back, is I have a Bunsen burner going here. And so we need to alter this. We know that this is combustible stuff, but it's not doing anything. Okay? So what can we do? We can change the surface area. Because really, if you look at it, if I pour some of this out, all this is fine particles of fat that should combine with the oxygen and do its thing. But sitting in a beaker, all piled up, I only have the surface area, what's on the top. That match goes in there, the oxygen, there's just not enough stuff going on. Okay? But if I spread it out and increase the surface area, then I get more of the combustion reaction going on. Again, spread it out, get more surface area exposed, and non-dairy creamer will burn. Oh, we're getting it covered up with non-dairy creamer. I'm losing my Bunsen burner. One more time. Expose it. There we go. I need to turn this off now. So that's it. That was just a hydrocarbon. And that's all I needed to do was spread it out. So more surface area was exposed, more oxygen got in there and was able to trigger the reaction. Okay? And it was just a normal combustion reaction. It's the same theory as to why if you're in a woodworking shop or at a lumber yard or something like that, that the saws and everything generally have a dust, or grain elevators and stuff have a dust dampening system, so that that organic material, that dust doesn't go around, because oxygen's all around. And all organic matter is combustible, would go through a combustion reaction. So they have dust dampening systems in like grain elevators when they're dumping in grain, and doing woodworking at the lumber yard and everything else when they're cutting up wood, and keeping that dust contained and down, because any spark could be very dangerous. Anyhow, there we go. That's just demonstrations. Your next video that we'll be going through will be looking at some of these different in a chemical reaction sort of lab way. But there you go. That should supplement your notes. Have a great day.